All right. Ah, yes, it's working. Good. I think we packed up, so I'm going to start anyway. I'm surprised. It's Friday afternoon, and it's the first time I see a meeting room packed in England. But anyway, so obviously for my accent, I'm not British, I'm French. And if you don't understand, don't hesitate to put a shame on me, and I will stop and try to repeat. Anyhow, I'm not going to probably use all the 15 minutes because it's a Friday, and I'm becoming kind of British myself. Yeah. So let's start right now. So we're going to speak about Reactive Stream. Who am I? I'm not going to take a long time to introduce myself. I'm just the guy that firing up laser. But I'm working for Pivotal. If you know about the company's former Spring Source, Pivotal Labs. And I'm also working on a Reactor, the asynchronous foundation for the GVM. And also, I'm a Reactive Streams contributor, which is cool because that's what we're going to talk about now. If you need to push any question, just harass the hashtag for the session or the handle, and someone will try to pick up the questions. Maybe me, maybe not, but some troll should reply to you at some point. So, we're talking in this session about reactive streams, which is defined as a specification. So there are a lot of questions about why we do specification again. Is it yet again another shitty manifesto, or is it going to be something very long to process and never end in something concrete like in JDK 10? No, it's not like that. But still, it's a specification. And in reactive streams, there are basically two major components, reactive and streams. Wow, I feel clever today. So what's reactive is, in fact? Well, reactive architecture, as defined by some interesting manifesto, which I recommend strongly, there is a link in the slide afterwards. The reactive architecture is essentially a new name for event-driven architecture, essentially. But there are some interesting aspects. I don't know if you can say you can find them in event-driven programming or not, but modularity is an interesting consequence of event-driven, because when you go event-driven, you react on signal and just break the strong link, the strong bound you have between two application codes. You don't ask for your logic to execute straight away. That's a nice aspect, a modular aspect. Another interesting property of event-driven architecture is it might be scalable in a sense that you react on event and you can add more consumer to react on events transparently. So that's an interesting property for event-driven architecture. And available because if one of these consumer go down, the interesting fact is you can have more consumer to pick up the demand and your application still works. So it's interesting to have all these properties derived from event-driven architecture. And they're all tied together. Availability and scalability, for instance, are very tied. You can add more consumers, but as soon as you add more consumers, your application becomes transparently scalable and available because the more consumers just pick up the demand. So my rumbling here is maybe not clear enough. I'm not going to focus in this presentation about reactive programming and reactive architecture, but the good description is here in the nice manifesto, in the reactivemanifesto.org. And an interesting aspect of reactive architecture is, interestingly, it fits very well with functional programming because functional programming is all about stimulus. You react on logic. So a stream. In reactive streams, there are many description and definition of streams, but the stream we think as commonly used, at least the stream we use in reactive streams, is a stream of data sequence. So just represent in your mind just a suite of mouse click, for instance, or trades, or whatever, in fact, some operations. But a stream is also, by nature, very interesting for its transforming API, because, well, I guess you all know about complex event processing and all these kind of patterns to process logic all on demand. Like, I'm receiving a new user. Should I subscribe this user to a new service, to a new database? And then after that, I retrieve a new object. And after that, I forward this object to the response, the HTTP response. So that is a streaming chain, a transformation chain. And that's one of the fundamental properties we think in stream. And the common mistake with the common confusion between stream and the other structures, mainly collection, is, well, the main difference is not a storage. Is not a storage. You can have a buffer, but the stream won't have a collection. In fact, an array will not store anything inside the stream container. So it's definitely not a collection. Sorry. And there are two flavors on streams, and that's very important to understand the differences. There are hot stream and cold stream. We think about trade and tick on hot stream because it's a real-time source. You don't have to wait for a subscriber to consume this source to generate events. Just the ticks are just ticking, and the trades are flowing whatever you subscribe or not to the stream. But there is also the cold stream, which applies necessarily on source you can replay, for instance, file. If you want to read from the beginning, the subscriber, in fact, will receive all the content of a file. So that's a cold stream, because any subscriber, whatever the time they use to, whenever they subscribe to or connect to this source, will, in fact, generate the same sequence of data, which is the core thing about stream. Another interesting thing about stream is its batch nature, its batch processing nature. So one thing you can think about when you do streams is transferring data, for instance, batch of data. So we know some frameworks already do this kind of thing. I'm thinking about Spring Batch right now, but any kind of thing that do collection, aggregation, and then reduce, like MapReduce, do this kind of thing, anything like that is it's some sort of batch processing. And the stream, by nature, is some sort of batch processing if you start using transformation operations like aggregation. It's very useful also for metrics, because, as we said, we have hot stream, and hot stream are very interesting in the metrics and the statistics universe, because when you start generating metrics, you're not necessarily waiting for this metric. You just capture the latest snapshot of the metric. So having a metric as a hot stream is very interesting for this reason, because you just capture metric events. You don't necessarily run for instance, your dashboard displaying your metrics. Every time you just pick the latest value as a gauge, for instance. So that's a very interesting use for stream. I guess since we are in London, we could also define trade processing as well, like something very useful for streams. That's definitely one of the use cases for the streaming API in general. And event handling, more generally speaking, in fact, when you create UI, reactive streams are very used in, well, very famous in the UI universe, because you can, well, mouse click, for instance, all user events are events you can define and process and consume. What do you do with a mouse click? Do you want to throttle the demand? Do you want to only have one click for every minute, for instance, or every 10 seconds because you don't want to double click? Do you want to filter some duplicate? All these kind of transformation operation apply super well in the UI universe, and that's something Stream API can define as well. So an interesting thing about the stream and the reactive stream specification is it has to be reactive. So it has to be compliant with two major properties. That's two properties described in the reactive manifesto, in fact. The first thing you have to be sure is that your reactive system is resilient, which means if a node goes down, if a consumer goes down, it shouldn't impact as much as possible the other consumers. So we also call that bulk heading, especially error bulk heading, but it's quite an interesting property of a reactive system. Modularity as well is very important. If you need certainly you need encapsulation if you want to become more and more resilient, and that's all the rage with microservice architecture. The component just becomes smaller and smaller, so it's easy to recover for a component failure. It's faster to start. You can add new functionalities quicker than usually with a monolithic application. So modularity is quite important for resiliency as well, which is a must-have trait for resilience and reactive system. Then, the other property, I don't think it's a must in fact, but anyhow, normally, it all depends how you call scalable, but normally a reactive system is meant to be scalable by, well, if we come back to slide 1 about reactive architecture, we saw that decoupling the demand and having the capacity to add consumers is also by nature a possibility for you to add scalability and scaling up. If you add more thread consuming your data, you scale up because you consume more processors for use from your CPU. If you want to distribute the demand across nodes, you scale out, and that also because you added more consumer, especially because this consumer will be a node, not a thread. So you can see that the resource in reactive stream is not necessarily tied to the notion of threading. It's mostly tied to the notion of dedicated context, assigned context to a stream. And that's why we talk transparently about CPU or nodes. The consumer can be one of them without differences. But the models matter because you will have to cross boundaries at some point when you talk from a producer to a consumer and they are living on different assigned resources. You will have to pay a cost to transfer the message from the producer to the consumer. And that's why choosing the right model matters. So there are a list of things that can affect you when you do this kind of transport. So context switching, if you deal with a multi-threaded application. Message passing itself is quite hurting if you don't choose the right structure. If you start using, I don't know, a synchronous map to pass messages, it's not going to be fine for your application. But there are also interesting resource costs in the JVM about creating more threads. It will take for you more memory, and well, creating threads indefinitely doesn't scale, and that's it. So one of the interesting patterns emerged the last years. I'm not going to focus on that, but actors are interesting because they solve two of the common issues you have when you deal with concurrent application, locking and context switching. So you won't have a lot of actors. You will have probably a lot of actors, but they won't use all of your thread memory. They will try to stick with a thread pool rather than using as much thread as it can, even if it could eventually, but that's not what the model is designed for. And the interesting property is agent protect as actor, sorry, I use the term agent, which is interchangeable in fact. Actors are like agents protecting the data, and so you're sure you don't have to deal with nasty thread-safe coding to share the structure between a producer and a consumer. In fact, all of that it's by design here with Actor. Another interesting pattern is non-blocking programming, which is slightly different from Actor, in fact, because non-blocking programming is a more general use pattern, in fact, because you just produce, you just have to be sure your code is lock-free, basically. And not necessarily all Actor implementation are lock-free. You have to deal with some locking to push the message in a kind of shared structure. But non-blocking programming just forbids that. If you take a good example of that, LMAX disruptor is something you can call a non-blocking programming framework, because all the point about the ring buffer is it's a lock-free structure. You never ever lock when you push your message in the shared structure between your producer and your consumer. So, well, I'm quite a fan of the LMAX disruptor implementation. It's all, if you look at the link, it's 2011 years. So, well, it's still in use and it's still evolving. We are now in 3.2.1. And that's, I think, quite interesting to look and see how they did achieve this kind of lock-free structure. Mechanical sympathy is a lot used by LMAX disruptor as well. That's one of the nice patterns you want to use when you want to deal with very efficient, high-volume message passing. So mechanical sympathy, for instance, is about false sharing between the producer and the consumer memory structure. So false sharing means you optimize your CPU hops exchanges between producer and consumer, which is, well, one of the bottlenecks you can ultimately find in message passing between a producer and a consumer. How you deal with the structure sharing, even at the core, at the CPU level. All of that is dealt with Brio by the LMAX disruptor and ring buffer. And, well, all sort of decoupling mechanism will have two ways, in fact, of implementation. So the push one will be about non-blocking or functional programming, because you just react as soon as there is something, you don't wait and pull. And queue-based decoupling otherwise is the opposite, and you will have to just wait and drain a queue somewhere, eventually every XX millisecond to do something. But that's super fine if you deal with slow services, because you can be sure that you will have to have a proper queue system to buffer the demand. In the case of a slow service, a slow subscriber means a producer will produce too much data, and this data has to wait somewhere. So queue-based systems are very interesting for these implementation issues. So, after this quick overview of both of the components of Reactive Stream, let's talk directly about Reactive Stream specification. The first thing the Reactive Streams define is the fact it's a non-blocking sequence, and especially an asynchronous non-blocking sequence. So what does it mean? That means that the specification will define anything possible to transfer asynchronously data between a producer and a subscriber, and the action of transferring this data must be non-blocking, meaning lock-free. Another property defined as one of the 4 pillars of Reactive Streams is the minimal resource requirement. All implementation of Reactive Streams must be lightweight, in the sense that, well, the definition of lightweight can be very personal, but in the sense that normally calling any method provided by the API should not prevent or negatively impact the producer of these events. So that's quite linked to the non-blocking processing of events, but that means when you subscribe, this operation, for instance, must be quite lightweight, must not impact negatively the performance of the caller. So there is definitely there is something interesting about Reactive Streams. It's not only about Java. Reactive Streams is an interoperable protocol, which means the specifications does not mandate the use of threading mechanism in Java, for instance. It can be applied directly on transport level. So for instance, we could apply, we could decide for network stack TCP, how it will behave, how it will implement if you wanted to use the reactive stream specification, because TCP, if you think about it, is another form of decoupling. It's another asynchronous boundary between two applications, except that happens at another level between nodes or between applications. And that's important to define the same kind of contract we're going to define inside the application and also outside of this application, because in the end, if you have the same contract, well, inside your application, you can rely on back pressure coming from your nodes, for instance, because the protocol implements as well the reactive streams, and vice versa, in fact, because you won't push data across nodes if the consumer on the target node is not requiring any data. So the reactive stream implementation could work across many technologies, not only Java. And the main thing about reactive streams, because it's not only about flowing data, it's not like just a channel. It's also, the main thing is also about the flow control provided by reactive streams. And we see what I mean by flow control just there. So imagine you have two components, two major components in your application. It's quite common, quite standard denomination, publisher and subscriber. So the publisher will push data to the subscriber, will signal data. However, if the subscriber doesn't have data capacity, or for some reason needs to throttle back the producer, ask the producer to produce less data, how can you do that? Well, that's a solution provided by reactive streams, which is quite unique in this context, because what a subscriber is going to perform is a demand signal. The subscriber will exactly say to the publisher at any point of time when he requires data, how much data he wants, and that's the main difference with the reactive streams implementation. So you can say at this stage, that looks like a queue-based system, because if between your publisher and subscriber there is some kind of draining mechanism that just batch drains some data, there is some kind of staging area somewhere between the publisher and the subscriber. Now, it's not really only a queue-based system, although it can rely on that feature to do buffering. So when your publisher produces too much data for a subscriber, and the subscriber, for instance, a subscriber requests 10 elements, and the producer is trying to produce 50 elements. So for the first 10 elements, in fact, signaling demand from the producer is going to be free, because they are just going to flow to the subscriber using, remember, one of the core threads of reactive stream, non-blocking publishing, non-blocking producing. So the events are going to be signaled for the 10 first without any kind of buffering, directly to the subscriber. But since the subscriber has only requested 10 elements, it will have to request for the rest of the element, if he wants to get them. The 40 remaining elements, they are staging somewhere, and that's up to the implementation to implement a queue-based system, overflow system, journal. That's what we're trying to do in Reactor, for instance. We try to provide a flexible API to implement whatever kind of overflow you want to implement. And it's important, and that's why also it's interoperable, because when you start within your application, dealing with slow consumer is more easy codes than dealing with slow consumer across nodes if you deal with network transport, for instance. And in that case, that's why we have TCP. There will be probably some kind of buffering happening at some point, because you have to wait for your consumer to be ready to read if you don't want to overflow your system with buffered data. And that's what reactive streams is trying to give to you. It tries to be more clever about data transport and what you can pass or what you cannot pass immediately. Another interesting property about signaling demand is, well, if you want to scale the demand, you can change it because it's all dynamic. Every time you need data, you need to signal it by using a method we see, and we need to provide a number, how many elements you want to signal, to receive at some point. If at some point you detect that your subscriber is consuming very fast, and the producer will never queue anything, that means you have capacity to add more demand, so on the next request, you will request more than the previous one. That's a kind of automatic buffering you can implement in this way. And, well, if we go back to the flow control, you can see an interesting thing happens then if you have two concurrent subscribers consuming data from a single source, a single publisher. You can see, well, I don't know if you can't see it really. Yes, the arrows in the connection between subscriber and publisher are bigger because the subscriber is picking up demand faster than the subscriber above, and that totally tolerated by the reactive streams. It's meant to have independent. A subscriber is an independent resource, or can be, and well, it's not necessarily an independent resource. There is an exception note about that, but necessarily or usually is an independent resource. So a subscriber can totally have a different rate. If it's two nodes consuming from a producer node, one of them has a faulty network or is having less resources, CPU resources or memory, is going to consume data in much less rate than the other one. So remember, I just talked about the reactive streams, nice aspect of signaling demand dynamically. That also allows you for batch publishing optimization. If your publisher knows how many data is ready to be accepted by your consumer, one of the things you can do, well, package, aggregate all the data in n size. The n size is a requested demand from the subscriber, and send them in a batch array, for instance, in a batch array or in a batched map or whatever you want to group your operations. And that's very interesting for, well, batch processing, high volume scalability, and these kind of issues. And, well, the data sequence in this case in reactive streams will be different depending on the use case you're implementing with reactive streams. If it's a hot stream, like Vert.x, you will see the sequence data you will observe will just be the one you will, the one emitting from the time you just subscribed, because all data subscribed passed before you have been passed to somewhere else, or maybe to no one, but you were not here when the data was flowing. So that's the definition of hot stream. You just see at the given time you subscribe. And the cold stream is the opposite, in fact. Every time you subscribe to a cold stream, well, you replace the data because the stream has the capacity, the publisher has the capacity to replace the data. If you see that with a file, you can just replay it from the beginning of the file if you want to for each of the subscriber. And a thing that is not defined by the reactive stream specification is transformation. So when you think about streams, we think about operation like mapping, aggregating, windowing, this kind of operation apply directly to the stream. But the reactive stream specification does not specify any of the transformation. It's up to the implementation to implement them. But reactive streams has a dedicated component for operation chaining called processor. So processor is in fact a publisher and a subscriber. But you can think about all these guys talking about RxJava and Java 8 and say, shit, why have we again another thing, another technology to look after, surfing the hype of reactive streams or whatever, it's that reactive thing. And well, the wondering is fine because they are called the same name, so that's very confusing at some point. Java 8 is the streaming API coming, Java util stream comes with Java 8, but there is a major difference between reactive streams and streaming API in Java 8. If you look at this Java 8 code, we take a stream, a call stream for widget, and from this stream we apply 3 operations: filtering, map to int, sum. And these operations are push operation except for the last one, which is a pull operation. So you can see it's black or white because every time you call .filter or .map to int, what will happen is an eager fetching of the collection, still pushing the data over the operation, but it's not necessarily what you will do if you will deal with asynchronous system, asynchronous boundaries. And moreover, the last operation is certainly not something you will want to do from a consumer producer perspective, because the sum operation is blocking, if you can see. .sum will return immediately a sum. So it's definitely different from the Java 8 in the sense that Java 8 is targeted at transforming operation, and that's super good. The thing is, you can't reuse the operation like you want. For instance, there is no generic lift operation that allows you to just call something and pass the result of this something to a downstream element. No, you just have to use one of these operations: filter, map to int, or whatever the collection is of operations. And RxJava is much more evolved in that sense that first, the number of transformations is just huge. It's based on reactive extensions from Microsoft, and you can see so much different operation from windowing to mapping to parallel processing to merging, zipping, all these kind of things, all defined. There must probably be more than 200 different operation transformation in RxJava. I haven't counted, to be honest. It's also not like the Java, even me, I'm confusing. The Java 8 stream, it's event driven. RxJava has 3 predefined signals. So if something is failing, your downstream component will be notified because there is an on error signal. If a stream is finished, you will be notified downstream with a complete signal. Also, RxJava has a flexible scheduling in the sense that you can create your own threading resourcing implementation if you are not satisfied with the default synchronous and asynchronous implementation provided by RxJava. You can say how RxJava will flow the data over your resource by implementing a scheduler. But there is still something not available straight away from RxJava, which is the dynamic demand nature. So remember all this thing about demanding 10 elements, and for this 10 next element, you will be notified directly without blocking. But if there are more elements, they're going to be buffered somewhere because you have to buffer. Some subscriber will be slower than the producer at some stage. So you don't want to block your producer producing data. You have to get this staging area between. And this boundary is something missing in RxJava. That's why, before a quick example. So what you do usually with RxJava is just using the observable API to transform an iterable or whatever you want to transform. You can also, that supports also old stream. It's not necessarily a cold stream. It's just in that case I observe a cold stream. And then you attach a subscriber, which are push operation for on next signal, on complete signal, and on error signal. But whenever you type .subscribe, it will demand all data. You don't have control over number of data you will request with the subscription mechanism. But you can work around this limit. But out of the box, there is no boundary between the producer and the subscriber. So there are other examples as well. We have Akka, Reactor, Storm, Vert.x. Akka has a new framework called Akka Streams, which is exactly the reference implementation for the reactive stream specification. But they all deal at more or less level with reactive streams. Vert.x, for instance, is a non-blocking I/O server and can stream data as such between a producer, which is the client node, for instance, and the server, which is a subscriber, and vice versa as well. Also, streaming compares to Spring integration camel in the sense that it's very close to enterprise integration patterns if you take in account mapping and other transformation API or filtering, for instance. So between companies, we have decided to come with a solution together. These companies include Netflix, TypeSafe, Twitter, mine, Pivotal, Red Hat as well, and some individuals like Dougley, who is behind the implementation of Thread Pool Executor and JDK. Why do you want us to see joining efforts at some point? Well, because of this. Imagine, well, all of these frameworks have a use at some aspect. I like the Akka. I'm a Reactor committer, and I like the Akka distributed system nature. The ring is quite well done and implemented. If I had to implement a cluster today, a cluster with application, I would definitely go for Akka. Also, the RxJava applications are very rich in terms of what you do with the event, with the data, and one of the interesting thing you can do with RxJava combined with other frameworks in Netflix like Istrix is doing matrix pipeline. So with asynchronous system, metrics become one of the core issues you will have to deal with, knowing which component has received how many events is very core because, because you lose some guarantees doing going asynchronous, and all these components, micromanaged components, need to report to something, to someone, to see who is not scaling properly, who needs to be cloned across more consumers. So in that use case, the use case is quite simple. What would you do with 4 implementations, different implementation of reactive streams? Reactor has a lot of implementation in data driver area. There is a Reactor data module, and there is an implementation of coach-based Reactor driver as well. So it's very good for implementing asynchronous data access, for instance. Well, this one is replicated on all over your nodes, and these nodes are managed within the Akka distributed system. So when you submit a message to Akka, which is going to be done by your Vert.x server, which receives produced demand by a client, just refreshing the page and subscribing to the response to forward to the subscriber or the user who pushed the data on the page. So this guy is going to talk to Vert.x, who is going to submit the demand to the cluster hosted by Akka, which on each node is going to ask on Reactor data drivers. And all of that is monitored using Istrix, for instance, and bridged by RxJava, who will take all the events and transform into metrics, interesting metrics for your applications. So that's exactly the use case for building reactive applications today. All of these components are now safely implementing non-blocking programming. They propagate demand each other without being the same technology, which is awesome on some aspect. It's just a kind of protocol. It is a protocol. And why we do have all this reactive application, it's simply, well, once we implement all of that, we benefit ourselves, for instance, in Reactor from implementing such reactive stream because it gives a clever pattern for us to communicate between our own producer and subscriber implementation. Also, well, we had to join together because if we had to write a standard protocol picked up slowly by a different implementer every time, it's not going to scale properly. Successful protocols are just protocols used by more than one person. And beyond it will work beyond the JVM. We already started discussions, so I dream about seeing this kind of thing implemented in Erlang, implemented in MQP protocol, for instance, this kind of thing, because they also separately deal with back pressure. But what would be great is the system deal together with back pressure. And so the reactive streams are, in fact, very simple. Just for now, it's 4 interfaces hosted in a jar, just a jar module. You can download through Maven Central, links provided afterwards. It's also defined by a single document with all the rules. We are currently reshaping this document, so bear with us. But the most important thing is what makes it more successful, what could give them more chances to be implemented by people and used and trusted by people is it comes with a TCK. And you know, there are a lot of API, a lot of SPI provided, you're just using an API and an SPI. Just using a few classes, a few interfaces, you implement the contract, all is good. You make sure you have read the commands, the Java doc, and say, okay, it should do that, so I will implement it that way. Now, it's not, we need to prove these things at some point, and the TCK is here to prove that your implementation is a valid reactive stream implementation, meaning that all the behavior described in the rules are going to be here, and that's it. You can expect your subscriber coming from Akka to be asynchronous, for instance, because it has been verified when they pass the TCK. Same for Reactor. You can define if the cancel operation necessarily cancel everything, clean the references for a subscriber, because you can cancel a subscription between a producer and subscriber. All of these behaviors, they need to be verified, and also it makes a good suite free for you to add in your project. Automatically, you test your implementation without having to deal with too much specifics. Well, you will deal with some specific to see the difference between you, to test your difference between you and the API to close the gap. But having for free 100 tests coming in your application because you implement the reactive stream contract, it's just cool. And so this interface is simple in the sense that there is no big ceremony, there is no lot of objects to implement. There is just a publisher where you subscribe the subscriber. It all makes sense when you see the specification. It's all about the asynchronous boundary between a publisher and a subscriber. So you can see as well the subscriber as operation very much like RxJava, for instance. In addition to that, there is an unsubscribe operation which can be used because the unsubscribe receives a subscription, which is something we haven't talked about yet. The subscription represents the unique link between a publisher and a subscriber. And that, on this link, you will interact. That's a protocol you will interact with to signal demand. That's where you will start saying, okay, I want 10 elements, I want 20 elements, because you see there is a request operation. And there is also a cancel operation, because at some point you want to clean resources. You don't want to leave your producer producing things if no one is interested into your data. So that's the protocol. An important rule is the subscriber can't receive at the same time, using, for instance, multi-threading, notification, for instance, one on next and one on complete can't come at the same time. It's prohibited by the specification. That's one of the things tested by the TCK, for instance. The subscriber is not necessarily, I was talking about asynchronous and isolated subscriber earlier, but it's not necessarily the case, because sometimes you want to avoid crossing the bound, the asynchronous boundary between the publisher and synchronous operation. I.e., for instance, if you do just a simple map, transforming your data into a JSON object, if you deem it too quick to pay the cost of an asynchronous boundary, you can leave your subscriber synchronous. You can just implement subscriber and implement the for methods, like we saw in the example about RxJava, and subscribe the subscriber to a publisher, and that's fine. The asynchronous boundary will be handed over by the subscription, in fact, so you don't have to deal with it on the subscriber itself. And the protocol is just simple as that. You start with on error, possibly, so you see it's a or condition, because when you subscribe, something can happen. Your publisher can reject the subscription. In that case, the subscriber, in that case, it will just call on error on the given subscriber. Or, if it worked, that means it's a sequence of unsubscribe, because if the subscription is successful, we call unsubscribe on the subscriber, giving it the ability to signal demand. And afterwards, we have a series, possibly between 0 or infinite, of on next event signal. And in the end, eventually, if the flow has to go to an end, remember there is support for auth streams, so not necessarily for a trading system. You don't complete a stream necessarily in a trade system because the flow keeps going on. But there is also a terminal state for errors. If the subscriber fails at some point, you want to be notified quickly rather than lately. So that's it. On error, or just unsubscribe and end on next. And if there is an end, on complete. And the asynchronous boundary can be ultimately very rich. Resource 1 can be a thread, resource 2 and resource 3 and resource 4 as well. The reactive stream implementation allows you to do this as well. You can execute the filter subscriber or processor directly on your first resource, first thread, or first machine, depending on what is a resource for you. This pattern also works as well. Sometimes reading from an IO selector, you want to just leave it free from any blocking because you want the next element coming into this NIO selector to be picked quickly. So you just discard asynchronously after the NIO selector. And concretely in Reactor, it could look like that, but this operation does nothing if you look at it. Mathematically, it does nothing. In fact, it creates a processor. Remember, a processor is a subscriber and a publisher. And it creates, in fact, it creates a subscriber and publisher that does nothing because the first thing it does is doing nothing. Pass-through action is no op operation. We configure some optional environment variable like prefetch, the batch size you want to use, and environment, because there is a concept of environment. But afterwards, we have a series of operations actually doing nothing at all, but returning the same thing every time. So all of that is just nothing. And you have, in the end, an identity processor, which is processor integer, because it receives integer and produces integer data. But this processor can also be used then on the stream publisher. For instance, I create a publisher based on 1, 2, 3. I just want to subscribe the previously created processor. I subscribe it that way. And yep, finishing with some example. We cannot, so remember, stream is tied to resource, but doesn't prevent you to do concurrent stream processing. So often implementations such as RxJava or Reactor come with dedicated method to do parallel processing. Parallel in that case is interesting because it will partition the work with the number of threads, depending on the dispatcher you provide. And the next operation won't receive the element you thought it would have received, but receive a stream of these potentially typed elements, because in fact each stream passed and there will be up to n thread stream, are partition you will run your work over. So each stream can be seen as a different thread. In that case, map is going to be thread safe, reduce, thread safe, consume, thread safe. And we talked about call stream since the beginning, but you can see in that case with Reactor, it's an easy way to provide an out stream as well. We don't just define any initial values. And on the different stream, you can just call data, you can produce data by calling broadcast. So that's it. The resources are available on reactivestreams.org site. Currently on Maven Central, we are on 0.3 release. We're working on the 1.4.0 M1 because we need 2 milestones, one for the types and one for the TCK. This release is about improving rules visibility, so as soon as we merge that, it will be even easier for you to pick up the implementation. The simplified types presented in this presentation are coming from 0.4 because before that we had 2 additional interfaces. And that's it. Currently, Akka Stream implements 0.3.0, on branch in Reactor, Reactive Streams implement 0.4.1 M1. RxJava and Vert.x teams have started the work, and they contribute a lot into the specification as well. And that's it. Any question? Yep. Yeah. Yeah.
Are there any people from the projects, from non-JV projects involved in that conversation?
I know there is well, everyone is welcome to participate in the conversation. It's why it's on GitHub. It's an open specification. It's not the process where just the company I've listed are involved. Everyone comments on the specification. Casing, I don't know how would you say that, is participating in a discussion about the network discussions. Todd Montgomery is also discussing about that. But if you have ideas, just go into the GitHub and there is issues. All the issues are used. We use the GitHub issues basically for discussions, specification change. And bear in mind it's 0.4, so we all are all early adopters in that case. I don't know if that answers your question, sorry. Does it? Yeah? Yeah. Right, no. Not yet, if I understood correctly. Sorry, I didn't pick all the questions, but I think the no is the answer. Any other questions? Good. Well done. Thank you for having stayed up to Friday 5 p.m. Thank you so much. Cheers.